The most significant cosmological discovery of the last 30 years is also the most mundane. We're not special. There was a time when we thought the heavens revolved around us. Today, we can safely assume there are trillions more planets out there in the darkness, and odds are there's alien life on some of them. I'm Dawn Nakagawa, the president of the Berggruen Institute in Los Angeles, and this is Futurology. For most of history, we'd never seen another world beyond our solar system. Then, in 1995, astronomers found one, a planet orbiting a distant star. Recently, the pace of such discoveries has picked up. We can now spot nearly 6,000 more worlds from our vantage point here in the Milky Way. So the next question is the one that would truly rewrite our collective cosmology. Is there anyone out there? But we only know what to look for on other planets by looking at what's happened here on Earth. After billions of years, our biosphere, which we are very much a part of, has irrevocably suffused our world with traces of life. If we can assume that any flourishing of life anywhere leaves a similar tint, then we should be able to detect it, even at great distances. And we don't just occupy this planet, we shape it. In the blink of a cosmic eye, our biosphere evolved a technosphere, a planet-altering rush of chemical and physical proof that we humans exist. Adam Frank is a leader in the search for signs of smart, capable aliens on distant worlds. He does this by using our most powerful telescopes to stare at a star and wait for an eclipse. In the brief moment that a distant planet eclipses its sun, faint starlight filters through its atmosphere, tinting the air with a unique chemical fingerprint. Those photons arrive here and register as a few pixels with a distinctive glint that could change everything. Adam won our Institute's first annual essay prize with a beautiful meditation on this search and the coming of yet another Copernican revolution in the way we think about our place in the universe. At our planetary summit in Venice, he spoke with Claire Webb, director of the Institute's Future Humans program. And now, Adam Frank and Claire Webb on Futurology.
Hey, Adam.
Hello.
Nice to see you.
Good to see you too, Claire.
You're an astrobiologist and a physicist. So tell us about how you do research at the intersection of those two fields.
Well, I started off, my training was as an astrophysicist, a theoretical physicist. And so, for the first chunk of my life and when I was certainly young and trying to get tenure, I was doing straight astrophysics. I was doing computational physics about how gas clouds collapse under their own weight to form stars. So most of my career, or at least, the first 2/3 of my career was in straight theoretical astrophysics, asking straight theoretical astrophysics kinds of questions like the formation of stars, the death of stars. I started getting into astrobiology in a kind of roundabout way, actually. I'd always been interested in aliens, because I was always interested in science fiction. That's why I got into astronomy. But, when I was a graduate student in 1988, and, those years, there was no astrobiology for reasons we can talk about. And it was really through my writing, actually. I was working for NPR, I was, doing writing for NPR, and they asked me to do a project about cities, about the physics of cities, because they were doing a whole thing on cities. And I did it, I did one level, the physics of cities from the street level, and then I did the level from the rooftop, and then I did the city from space. And that was, I started thinking about the astrobiology of cities and climate and such. So that is sort of where the pivot began. And then I first started looking at how the atmospheres of exoplanets, we discovered all these other planets. I started looking at how they behave from a physicist's perspective, and then I started asking about life, and I started thinking about biospheres and technospheres. I started thinking about how life changes planets. And that took me in a whole other direction, not specifically biology, like I wasn't studying cells. That kind of came later. But just thinking about the impact of life on planets, either from the biospheric point of view or technospheric, like, once you build what we're building.
So it is this recursive loop of evolution. And life is expanding as a category based on that point of view. So can you tell us a little bit about how you see the relationship between the biosphere and the technosphere, and what is the biosphere, and why do you make a distinction between the two?
Yeah, that's a great point. Because in some sense, let's come around to that. I want to make a distinction and I don't want to make a distinction, right? So let me just, if I can go all the way back and tell a story. Because all of this starts with climate change, right? My own experience of climate change, which is that when I got out of undergraduate at the University of Colorado at Boulder, I decided to take a year and a half off because I was tired. So I did all kinds of like weird things. I planted trees in British Columbia. I was a bouncer at the Rocky Horror Picture Show.
Oh my God.
At the 8th Street Playhouse in Greenwich Village.
I can see you being very intimidating to the hipsters.
Yeah, I can tell like people were. My main job was to clear the bathrooms because it was the midnight show of Rocky Horror Picture Show. You can imagine.
Oh, wow.
Yeah. It was
very colorful bathroom, I bet.
So then this is 1986, and I got a job at the Goddard Institute for Space Studies, which is a NASA installation on 113th Street and Broadway over the diner that was in Seinfeld.
Nice.
Why it was there, I don't know. But so I was, I was a scientific programmer. I was just doing whatever they told me how to do. And one day I asked my boss, like, what are we doing here? Like, what are we? And she sat me down and said, well, we think, this is 1986, right? It's possible that human beings are changing the climate. And we're trying to figure out how to find the signal of whether this is happening and what will happen. And I said, well, what will happen? And then she laid out like, everything that is now happening. And I remember walking out into Riverside Park being like, whoa, because she kind of just told me what seemed like the end of the world. So I'd had this knowledge of climate change, about the possibility since as a young man, even before I started my career. So it was always sort of sitting there in the background. And so now fast forward to, where I am as I'm starting to think about biospheres and technospheres, et cetera. Formally, first from, because NPR had asked me to think about cities as kind of a planetary scale phenomena. I started to kind of formalize. I wanted to formalize my thinking and try and model, because I'm a simulator, right? How could I model the interaction between, a civilization and a planet? And that took me to starting to think about what other people had thought in the history about just in general life and planets. So that's where you get in, where I was introduced to Gaia theory. Right? The idea that the biosphere, which is the sum total of life, right? The biosphere, which is a term that was actually coined by the great Russian biogeophysicist Vladimir Vernadsky in 1926, goes that far back. He was the one who recognized that the biosphere was a kind of, you had to take it as a whole. All the life, all the microbial life, the forests, had to be taken as a whole. And that it was a geophysical force. It wasn't just some, as I like to say, it wasn't just some green scum on the surface of the earth, powerless. It actually changed the evolution of the planet. And it was the Gaia theory that really worked that out in detail about how the life could hijack the planet. And Vernadsky saw this. They called it the noosphere back then. And there was Vernadsky's version, and then there was Teilhard de Chardin's. Chardin's was a little bit more like, pot smoking, kind of like, yeah, man, we're all connected. Vernadsky's was much more sort of like grounded scientifically.
Tell us more about the noosphere, because that was a particular idea that involved the biosphere, but also humans' impact and also intellectual impact, cognitive impact on the planet.
Yeah. So the noosphere, and the idea, no is Greek for thought. So Vernadsky, has this idea of the noosphere as being cultural energy. He had already recognized in 1926 that human beings were, through the creation of their technological infrastructure, would sort of begin to shape the planet on as strong a level as the biosphere had for billions of years. And he actually thought that, life had always been doing this. He called it cultural energy. That was his term. But he just said that beforehand there just wasn't much, there wasn't much to the noosphere until we arrived. So this idea of the noosphere is that, there's going to be this sort of cultural energy. The artifacts of thought were going to enshroud the planet and change the planet's activity and change us. Like we would become part of the noosphere. Like it's more than any of us, right? Each one of us contribute and are active in the noosphere, but the noosphere would become kind of a thing in itself. So it's a really potent idea.
And that reminds me of the work that was being done just before the founding of NASA by Joshua Lederberg and others who called themselves exobiologists.
Right.
That later became, of course, the field of astrobiology. Lederberg lobbied then NASA to consider also not just human and manned missions to outer space, which of course was a driving cause of what we now call the space race, but also think about life in space, even microbial life in space.
Right. It's really cool to see like these ideas that sort of were just starting on the ground, like somebody has it and they, so the idea of the biosphere, like, oh, here's this new word, biosphere, which now we're like, well, of course, the biosphere. But, the space race is starting. People are finally, the beginning to understand like, oh, we're actually going to be able to think we should, get into space. So we should have to start thinking a little bit more clearly about space. Whereas now what has happened, of course, and this is why climate change is so important, sort of the hammers on the head that, oh, you're a planet. You're living on a planet. You changed the planet. So ideas like the Gaia hypothesis and, all of this stuff suddenly starts to materialize, starts to become, more than just a few people thinking about these questions to kind of an urgency to dealing with it.
Moving from the concept of the biosphere, or at least integrating it with the concept of a technosphere, was also part of these conversations going on in cybernetics, which helped think of biology and technology as an integrated feedback loop. So can you tell us about that?
Should we talk a little bit about the Gaia hypothesis?
Yeah, let's
just
talk about
because
Gaia.
That's a really interesting story, because this was really part of it. And there's a little side bar that I think would be useful for us to talk about. Okay, so the Gaia hypothesis, James Lovelock is this, kind of polymath chemist who'd actually invented a device in the 50s that made him kind of independently wealthy, or wealthy enough that he could do whatever he wanted. And so lots of people wanted to work with him. And so NASA, it's 1960, NASA's thinking about doing missions to Mars. And so they hire him to hey, help us come think about missions to look for life. And he's sitting in these meetings and everyone's talking about looking for microbes on Mars. And he's like, how do you know there are Earth-like microbes on Mars? So this whole idea about what is life and how to detect life, he's thinking about. And this is the part of the story that I love. He was in the office he shared with Carl Sagan. Like Carl Sagan, when you think about all these stories, Carl Sagan just kind of pops up. He's like, where's Waldo? He's just like, oh, Carl Sagan's everywhere in this story. And so he's, it's in that office where he recognizes that atmospheres are the way to detect life, because if there's life on a planet, it will be so potent. It will, if there's if there's a biosphere, not just like individual life, but if there's really a biosphere, the atmosphere, it changes the planet's atmosphere as it did on Earth. Like there would be no oxygen on the planet if it wasn't for life 2 billion years ago inventing a new kind of photosynthesis. And it's from that step then leads him to recognize that life has the ability to hijack planets. So the Gaia hypothesis he develops from that is the idea that once life becomes thick enough, so to speak, once the biosphere becomes rich enough, there's enough life happening, that it will take over the planet's trajectory. The planet will evolve in directions that it wouldn't evolve without life. And that it will become homeostatic. That life will change the planet's trajectory to keep life happy, so to speak.
And of course, this was developed largely with Lynn Margulis. Could you break down what you mean by homeostatic and
Yes.
why that's important for all living systems, we think, and then just how kind of miraculous it is or innovative it is as a concept to apply to an object as large as a planet.
Right. So if you drop me off in the Arctic, right, it'll be cold outside, but my internal temperature will still be 98.6 degrees Fahrenheit. And if you then drop me off in the Sahara Desert, where it's 110 degrees, my internal temperature will still be 98.6 degrees. That's homeostasis, that the body self-regulates. No matter what's happening to the conditions outside, my body keeps my internal conditions in a range that is good for me to stay alive. So the idea of planetary homeostasis, that no matter what happens, to the environment of the planet, now here it's like a good example of changing environment, the sun is slowly heating up. The temperature of the sun is slowly heating up such that $3 billion years ago, the planet should have been colder, significantly colder. But the idea of Gaia was that the biology, the microbial systems produce feedback such that as the temperature of the sun warms up, the planet, the microbes will do things to make the planet more reflective. So it'll bounce more light off to keep the temperature of the planet the same. So that's the idea of Gaia.
And it's, and it's another way to kind of tell the story about the planet and how stories are deployed. There's still being false narratives created around climate change, much to human detriment and planetary flourishing.
Right. Well, and I think, if one of the things we want to talk about is sort of this idea of how if humanity is to make it through this, and it's not at all clear that humanity is going to make it through this. It's not clear. One of the things I worked on was the idea that this transition that we're going through may be universal. Any civilization that starts harvesting energy from their planet. We did a whole series of papers modeling this. Any civilization that's climbing up the curve of technological sophistication harvests energy from their planet, puts it to work, and thereby the second law of thermodynamics, which tells you that, there's no free lunch, is going to affect the planet, is going to push back the planet's climate system, is going to respond to all that energy being used. So in order for us to make it through this, it's about new stories. It's about having the right set of stories. Can we change the stories we tell about ourselves in such a way that, when we talk about the planetary as a new kind of, cognition or a new form of conscious, a new kind of design for the human project, part of that is having stories that would make the building of new coal-fired plants unimaginable. It's like, well, of course we're not going to do that.
Yeah.
Right. So.
And how, so let's go back to the technosphere,
Yes.
right? That is really an important part of this story and your story, the story of the planet, the planetary. You said earlier that you were bridling a little bit at the distinction between the biosphere and the technosphere. So how does the technosphere operate also within a biological register?
Yeah. Okay. So let's first do this sort of where I get riled up about. There's a certain narrative with climate change and thinking about the human beings on Earth, which is that we suck, Oh, human beings, we're a disease, we're a virus, the Earth can't wait to get away from us. And I'm like, I just find that kind of a dumb and pointless idea because essentially, we are, meaning we as a technological civilization that's building cities and doing all this, we're what the biosphere is doing now, right? So the biosphere is this incredibly creative, engine, so to speak, that, for a while it was like dinosaurs. Hey, everybody, let's see what happens if I put dinosaurs on the planet. And then I don't mean to, anthropomorphize it, but it was, and then it was the experiment or the new innovation was grasslands, like prairies. That was a new biospheric innovation. And it was like, oh, what happens if I do that? And right now it's a technological civilization. What happens with that? So the idea that like cities are somehow nasty and forests are great is like, I just think really misunderstands what we are. The technosphere is a new innovation that the biosphere has produced,
Mm-hmm.
right? And so the technosphere, then we can ask, well, really, what is the technosphere? So, we can formally define it as that aspect of the biosphere which is artifice, right? Which requires a certain kind of reflexive intellectual or reflexive cognitive design, explicit design that, other biological systems on their own would not produce, right? So, that's a very complicated way of saying that, somebody had to make it, right? There's a particular species that has evolved that builds things with explicit design and purpose.
Well, what about bees or termites? Could you look at a termite mound or a beehive in the same ways that you were looking at cities in space and say, okay, this had intention behind it. This is how the termites or the bees are coming to know their own little world, and this is artificial? Or what's the distinction between the two?
Yeah, well, I would actually, I'm fine with seeing them as a continuum. I'm absolutely fine with that, because eventually what I'm trying to do in this work I'm doing now with the physics of life is to not make us so special, is to understand that, you know, all life has a certain degree of sentience, you know, going all the way down to bacteria. I would argue that even bacteria have a certain degree of sentience. You know, life manufactures its environment, you know, in certain ways. But there, you know, what's unique for us, at least in for as human beings, is the amount of energy we have per capita, right? That's what's changed. You know, when 200,000 years ago, every person got one person's worth of energy per day. Because of our particular cleverness, you know, this idea of artifice, our ability to build extensions of ourselves that many times are about capturing energy and using it. And sometimes that capturing energy was, let me go capture that cow and put the cow to work for me. That we are now, I did this calculation one time, the average American at least, has the equivalent of 50 servants, 50 other people doing, you know, from the plug in the wall. So that is, and I think that's maybe an important way of measuring it. You know, each termite still pretty much has one termite's worth of power. We figured out how to harvest energy in a way that has multiplied our individual access to energy.
Thinking also of horsepower. So, you know, I have a little Honda Fit, but I still have a ton of horsepower, you know, compared to some agrarian farmer a few centuries ago.
And that's why actually once you don't really get a planetary feedback until what you're doing has a significant multiple of your per capita energy, you know, your non-technological per capita energy. Because, you know, you got to harvest the energy. So that means you're pulling it from somewhere in the planetary system, and then you're using it. You're putting it to work. And so this whole idea, the beautiful second law of thermodynamics, which everybody should know because it's amazing, just basically says if I give you some energy and then you want to use that to do work, you know, you want to pull a lever, you know, raise a brick upwards, some of that energy gets wasted. Some of that energy turns into just like heat, you know, of the friction in the pulley. So there's always some waste. There's always some unintended consequence of using energy to do work. And so if you're going to end up using huge amounts of energy as a civilization, like, you know, because what is a civilization? A civilization is just a mechanism by which energy is turned into work. You're going to start having feedback on the climate systems, on your planetary systems. You're dumping huge amounts of energy back into the system, the planetary system. So yeah, of course you're going to have a feedback.
So it's funny that humans' effects at a planetary scale have been very destructive, and we learn more and more about that every day by the very mechanisms that we've built in the technosphere that is causing such heat waste, and that's a bad feedback loop. At the same time, because of the biosphere producing the technosphere, that's something that you describe as planetary intelligence, which seems actually, I've never thought about it before as having that kind of irony. So what do you mean when you say planetary intelligence? And how is that perhaps at odds with humans' individual stupidity?
Yeah. So planetary, what I meant, I think there's a certain inevitability, and we should be careful with ourselves. Like, again, this is a narrative of human beings suck, right? When we discovered oil, it wasn't like we were like, I will destroy the planet with this substance. We were like, this is awesome. You know, I can keep my house warm. I can use it to power to drive around.
The iconic scene in East of Eden. Yeah. You know, where he's like, the oil. That's what I was thinking of. Yeah.
Because it was a great thing. We've always, the whole history of humanity is trying to find ways to heat our cave, you know, like animal dung. Okay, fine, whatever. And then, you know, it took us a while to realize, like, oops, maybe we shouldn't be doing this anymore. And then, you know, of course, there are nefarious players on this, the ones who knew Shell Oil, you know, who knew that this was going to have unintended consequences. They're like, we don't need to talk about that. So the idea of planetary intelligence, it came from this paper that I wrote with Sarah Walker and David Grinspoon. And the idea was like, let's look at what happened to the biosphere. Let's look at the 3 billion year history of the biosphere and how the biosphere became Gaian. Right? How it exerted these feedbacks so that it could become homeostatic. It took over a whole planet. How did that happen? So if you look at it in the beginning, when life was thin on the ground, when there wasn't that much life in the origin, the first 500 million years or so, there wasn't enough life to really do the processing of the gases and the erosion, changing the way the land eroded, that it didn't have much effect on the planet. So we called that's an immature biosphere. Yeah, there's life there, but the biosphere hasn't formed this dense web of feedbacks that allow it to start exerting some control over the trajectory of the planet. Once you get enough life, so the best example is or once the life innovates enough, like the Great Oxidation Event, when some microbes figured out how to produce oxygen.
And without that event, we would never be here.
Yeah. So actually, what happened was the Great Oxidation Event was microbes figured out a new way of doing photosynthesis that actually allowed them to spread like wildfire, and the oxygen was an inadvertent. They were kind of farting the oxygen out. So then the biosphere became mature. Like the biosphere now fully exerted these controls over the planet. And that's when we talked about, at that point, it makes sense to think about the planet as having a distributed cognition, right? That there was cognitive activity in the sense you had all these networks of feedback loops of living systems there was information about the environment feeding through and response to the environment. Like if the temperature of the planet went up, these feedback loops kick in and they change the planet's temperature and bring it back down. So we were thinking about the idea of planetary intelligence in the framework of what is now called, distributed cognition. So there's a whole really cool field in what's called complex systems, looking at termite mounds and ant colonies, beehives, where the cognition, or here's the best word, liquid brains.
Ooh,
isn't that a cool idea?
It's really cool.
Our brain's kind of solid in the sense the neurons are just where the neurons are, but here, like each individual ant in an ant colony is kind of a neuron in a certain way. That's one way of sort of seeing it. Or this idea, we're not sure if it's true, but that an entire forest through the fungal networks that connect the roots is a kind of green mind, that the whole forest is kind of cognitive. So what we were asking is can this happen on planetary scales? Can this happen over an entire planet? So that was our idea, that the mature biosphere exhibits planetary intelligence. Right? So now let's go to the technosphere, and it's clear that we don't have that. We don't have. So actually, let me introduce a really cool term, key term, is what's called autopoiesis. Autopoiesis comes from the work of the great Chilean neurobiologist Francisco Varela and also Humberto Montoura. And that was the idea. I really love this because if we're going to talk about the physics of life later, you can ask what is life, right? There's lots of definitions and people tend to focus on, life reproduces and life has metabolism and life has genetic, inheritability. But what I liked is they focused on life is alive, right? That thing about being alive, that to be alive is to maintain yourself, to keep yourself being alive under precarious conditions, because at any, sooner or later it's going to end. And they use the term autopoiesis, which means self-creating, to be self-creating and self-maintaining. That's what separates life from a rock, a cell from a rock. And it's what separates life from AI, from machines. Machines, somebody else gives the machine its goal, its purpose. Life creates its own goals and purpose.
Yeah.
So one thing we want to really, especially the work I'm doing with the physics of life, is that life is always a community. There's no, even the first cell was not really the first cell. The whole planet, in some sense, Sarah Walker talks about this. A planet has to be ready for life. Like a planet already has to go through certain kinds of evolution in order, like mineral evolution, to be sort of even prepared for life to happen. So the idea of this individualist, let's just think of a cell. No cell So like once life begins, no cell exists by itself. It's always communities.
Yeah, and it's funny too that the cell has become this unit of life. And what I so love about your thinking, Adam, is kind of thinking of the planet as a unit, which is so much more ambitious and also contains the possibility for even a fluid kind of intelligence between two interacting planets. Perhaps in the past through panspermia, certainly when the protoplanetary disks were forming, and a lot of the same kind of starting ingredients were distributed across planets and moons in our solar system. And now, as humans, that the biosphere has produced, the possibilities of exploring other worlds and bringing our liveliness with us.
Yeah. Well, this is this idea when we think about life. So, I'm going to circle us all the way back around to the planetary intelligence and the idea of the planetary, which is, the Berggruen Institute is very interested in, is that what is required, what stands before us now is, we, in order to develop a mature technosphere, right? A technosphere that will be autopoietic and self-maintaining and self-creating, is that we fundamentally need a new vision of nature, right? A different vision of what nature is and what our place in it. And what part of that is going to be a new vision of life, right? Whereas what emerged out of the Copernican revolution, the kind of science that emerged out of the Copernican revolution, was one that by necessity, pushed us out of the picture. We just you were trying to form a way of how can I talk about the world in a way that is universal, and I can, create universal laws that I can then apply, mathematical laws that I can then apply to the world. And so in order to do that, it had to really get rid of subjectivity. The subject, the person watching the world, had to be pushed out of the picture. And the problem was it pushed it so much out of the picture that it forgot in the end that it was ever there, and then ended up demeaning it. Subjectivity. Oh, you don't want to be subjective. But the idea of life's place in its own story is central. You can't take life out of its own. Life is not a machine. Life is not, you're not a computer made out of meat. I'm not a machine made out of, out of bone. So this question of the self-creating, defining aspect of life is part of this new vision of nature, where life, the subjective, the interior part of life, life's, the loop, the weird loop, the chicken and egg loop that is life, is not pushed to the side, but actually becomes central to it. And so this is where the information processing, the memory, the knower of the information becomes central, where beforehand that was all pushed to the side. And you see this with AI. This is why what's going on with AI right now is so dangerous, is that we're getting this hype that we're right on the verge of a general AI that's going to be sentient. And in fact, that's being pushed down our throats by people who are going to make money off of these versions of AI. And it's going to be such a diminished version of, to be human, as you say, the surprise, the delight. To be human is so much richer than what these AI systems are capable of. They're great tools, but they don't even begin to resemble what we are. And you get all these people telling us, oh, no, this is already. So the analogy I like to use is self-driving cars, right? We've been promised self-driving cars for 10 years. We don't have self-driving cars. For a city like Venice, where we are right now, you're not going to get self-driving boats for them because it's too complicated, right? The world is richer than these formal systems that our AI can capture. But what we're going to do is we're going to get these systems shoved down our throats that are going to be, it's like the same thing of tearing Venice down and replacing it with a grid of canals, because AI could deal with that. As long as it's nothing but left and 90-degree left and right-hand turn, sure, it can deal with that. It's going to level our cognitive experience, because that's the best they could do, and they, need to make their zillions of dollars.
It's a approximation of information often leads to less richness of the experience of that information.
That's really what it is. Yeah.
So going back to, I'm thinking also yesterday of coming home in a water taxi and the tacit knowledge that I guess the captain of the little boat had, going backward and forward, like stepping on the gas, to get the boat just aligned with the dock.
Yeah.
That's embodied knowledge that's passed on through many generations. And also a human has to develop a feeling for a machine in order for that machine to work best. Okay, so how do you think this need for a new interpretation of what nature is and what life is and what life does is going to be important, perhaps crucial, for identifying strange life beyond Earth?
Can I actually step a little bit further back? Well, I want to say why it's important also for this idea of the technosphere and developing the planetary, right? So, we face this problem that, we're in the midst of the Anthropocene, and, we're clearly going to blow through 2 degrees warming. We're changing the planet in a lot of ways. And, we don't have this sort of conceptual story, going back to stories, about how to deal with this, how to organize ourselves. What's the design of a human civilization that can cope with and deal with both the consequences of and then also the causes of the Anthropocene and climate change. And so this idea of a redefinition of a new vision of nature, I think is actually essential for that as well, because it's about putting ourselves back into the story, right? Because the science that emerged out of the Copernican turn, out of the Copernican revolution, as we said, it pushed life. Life became an epiphenomena. It's really just all about atoms bouncing around in the void with the physical laws that govern them. And life is just like, whatever. Life's just, it's not important on its own. It's not fundamental on its own. And from that view, out of that, because it was so potent, arose a whole political and power structure. And that's one of the things, that I talked about in the essay that I did for Berggruen. And it had political consequences. It had economic consequences. And so we built a world where, you couldn't see, nature was invisible. Like, I look at a mountain, it's like the only thing that mountain is a bunch of resources that I can put a monetary value on. But the other aspects of it as an ecosystem, we're like, whatever, who cares? They weren't a fundamental import. The way it figured in our stories of the mountain was very secondary.
And the hour here is the dominant worldview, but it wasn't a total view of what the mountain meant.
Right. It was the dominant worldview in the sense that it dominated the political economy, which meant that the mountain would be stripped because the only value the mountain could be given was its economic value via its monetization of its resources.
Yeah, and this signaled a complete reorientation also for humans, how we thought of ourselves. And so Carolyn Merchant calls this, she's a historian of science, the death of nature.
Yes.
So it constrained what it meant to be human, along with which was completely continuous with the narrative to control nature, drain the swamps and actually, because that's what they did.
Cut down the forest, drain the swamps.
And mine the mountains. Extraction became the activity of control. Yeah, but let's go back to the Copernican turn and the Copernican revolution. That one could say is very much related to this cognitive reorientation of. It's another cognitive reorientation of what nature is and nature could be that's led us to where we are now. So let's go back. Let's go back to Copernicus.
Right. Because the things like the Copernican, the Copernican turn, the Copernican revolution, which was the initiation of the scientific revolution, was awesome. It had lots of awesome, amazing things. It led us to the miracles of the world that we live in today, as well as having some really, negative consequences, which we're now dealing with. And that's why it's time for a second. We're poised to have a second Copernican revolution, which is the kind of things I'm talking about, the new visions of nature.
But tell
Let's go back to the
who was that dude?
Yeah, who was that dude? So Copernicus was an astronomer. He did a lot of other things, but this was at the time the dominant model of the solar system and the universe was that the Earth was the center of the universe, and the planets and the sun and the moon all went around the Earth. And Copernicus pushed back against this for a number of very interesting reasons. But basically, Copernicus proposes a heliocentric rather than a geocentric universe. Sun-centric, right. A universe where the Earth is just, is in some sense, the Earth is dethroned. It's just another planet orbiting the sun along with the other planets in our solar system. So this was a very controversial idea at the time, right? He doesn't publish his book until he's dead. He waited until he was dead to publish the book. So then, in the 16th century, the 1500s, heliocentrism is a dangerous, heretical, to some sense, heretical idea. I mean, different things were happening. Church tolerated it in different places or didn't tolerate it.
And what's amazing, too, is that the Ptolemaic system of the universe, Ptolemy, this astronomer from millennia ago.
1,300 years it managed to, that's a long time to have your system.
That was the dominant view.
Yeah.
And what astronomers would do was to really shoehorn the data that they got from their observations into the Ptolemaic model of a terracentric solar system.
Yeah, people have a model and then they'll see the world through that model, even though actually they're not seeing it. So there's even the example of Aristotelian physics where you throw a ball, right? And so, we now know that when you throw a ball, it follows a parabolic path, a nice curved path. But the Aristotelians actually had this idea: you threw it and then it just dropped straight. So even though they could see it was moving in an arc, somehow they had to interpret that arc as being, a straight drop. So yeah, there's a way in which when you're locked in a paradigm, you see the whole world in that paradigm, even though actually you're not seeing the world. The data, you blind yourself in a certain way, which is a great thing for us to talk about because, one of the arguments I'd made is now, in this second Copernican revolution, this revolution that we need to go through now is that there are blind spots that we've gotten used to, that this new, we have to recognize those blind spots and open them up. And that's part of what will happen in a second Copernican revolution. But so let's just to finish the Copernican revolution. So Copernicus, has this idea and lays out this mathematical model with the Earth with the sun at the center of the universe. And that's what, Galileo picks up on. And Galileo with the telescope, he's going to argue, that it's a Copernican or heliocentric model, and then from that also develops this new physics that then Newton picks up on, which will be the basis. This is the birth of modern science. So 1600, the Copernican turn is really the scientific turn. Is to we figured out a way of entering into dialogue with the world. It was very much an experimental method, experimental approach, whereas the old view was no, Aristotle said this is just the way it is. So it's great. It's the discovery of modern science. It's what particularly, science. There was a lot of things leading up to this that were, that stretched across the globe that, lots of different cultures contributed to. But it was the genius of the Europeans. Every culture has its own genius. This was the genius of the European culture that put the final pieces here of the scientific methodology.
And it's so hard to shed preconceived notions about oneself and nature and the world. I'm thinking back to your example of Galileo. And so his notes in the Starry Messenger, they're so fun to actually read the historical text because he himself is kind of surprised. So he's looking at Jupiter and he's noticing what they called stars, but which we now think of as what we now know are we now call moons. That there were 4 of them, and they seemed to be trading places night after night, and it was because of the seed that Copernicus had planted that Galileo's observations led him to come up with a coherent theory of observation and what nature was actually doing.
Yeah.
Jupiter was the local center of gravity around which Io, Ganymede, and Callisto are orbiting, and if that's true, then Jupiter is orbiting the sun, and so is Earth. Galileo, and I think it's really important the social context too, to convince people, he was a very good politician. He was a courtier at the in the Medici court, who of course had enormous political influence, even really more than the Catholic Church, which of course they worked hand in glove. And so by naming these Jovian moons after, he wanted to name them after the Medici princes. He bought their goodwill, and that actually softened kind of the appetite. Yeah. So he did not suffer the same fate as Giordano Bruno. He was successful. He didn't wait to publish Sorry Messenger after he died.
Right. No, it's very true. And I'm very much aware of this idea of like being a heretic, because this book that myself and my colleagues, Evan Thompson and Marcelo Gleiser, wrote, called The Blind Spot: Why Science Cannot Ignore Human Experience. We felt we were being quite heretical because we're pushing back against, what is now the dominant paradigm in science of what we call the blind spot is sort of reductionism and a kind of naive physicalism, the reification of mathematical laws that, math exists in a Platonic realm. And we were like, oh, we're heretics, And then remarkably, the reviews have been very positive, and like, oh, no, we're like, nobody wants to set us on fire, I was like, oh, I'm not really a heretic. But it's very true, this idea that like, right, how, whether the community is ready for things, the communities you're arguing with, they're ready. And it's also about the stories you're telling about it as well. It's, there's this science, and I tell this to my students, is like, you're always telling a story. No matter what your data has, you're telling a story, and you want other people to listen to your story and find your story interesting and compelling. So you can never ignore the role of story.
So you mentioned that science fiction was a major inspiration when you were younger, and probably continues to be a font of inspiration now for your scientific work. So what's your favorite science fiction book, and how did it help you become an astrobiologist who wanted to illuminate blind spots?
So, if we're just going to talk about my favorite science fiction book, it's Dune. I mean, Dune. Yeah, I just watched Dune Part 2 again, and it's just, that book it's really hard to imagine. Like, what was Herbert doing? Like, that he created the cool thing about Dune that's important actually for astrobiology, or thinking about the work I do in technosignatures is Dune takes place 30,000 years in the future, right? The idea that there's been a contiguous civilization for 30,000 years, and on the one hand it looks very familiar, it's feudal. On the other hand, he managed to capture both sides of being familiar and also kind of like weird, dreamy, strange, that capacity. It's such a richly imagined universe of change and difference, and yet constancy. That if you just ask my favorite book, it's Dune. There's just no other source. But more recently, I've been reading lots of things. Two things. One, I've been reading a lot of since the mid 80s or 90s. Kim Stanley Robinson wrote this series of books about Mars, the Red Mars, Blue Mars, Green Mars series, which was a return of science fiction back to the solar system, right? Because kind of once we started actually sending probes to the solar system, science fiction kind of was like, the solar system, where, used to be in the 50s, everything was on Mars. And, that was a move where science fiction started coming back to what the solar system would happen in the solar system. Because, interstellar travel, I'm not sure actually. I'm not sure whether civilizations really do interstellar travel. It may be very expensive, very difficult, and because of relativity and the timescales, that you quickly become disconnected from whoever you sent there. You're no longer even part of the same species, or So, but the solar system is really, if you want to ask what the human future for the next 1,000 years, which is a long time, is going to look like. If we make it through climate change, it's the solar system. We will settle every nook and cranny of the solar system. We will take asteroids and turn them into rotating space habitats that are large enough to have Manhattan-style populations. So the Red Mars, Blue Mars, Green Mars series was this idea of this solar system that gets settled. And then there was the Expanse series by S.A. Corey, who's actually two authors, which was the most realistic, most sort of scientifically, accurate story about an inhabited soul. It takes about 300 years from now. And it's just a great, really, it's also just great science fiction. It's fun. It's a really fun story. And it's got an alien in it, but not really, that's not the it's not about the aliens themselves. It's certainly not in the beginning. It's about human beings and what will happen to it. What happens to us once we expand into the solar system. So that was really important for me for thinking about the human future. And then in terms of thinking about sort of civilizations and the paths they may go on, there's another author that I was introduced to named Cordwainer Smith. He was actually the guy who wrote the manual on psychological warfare for the CIA. But the cool thing about Cordwainer Smith is the whole series of short stories and books are called The Rediscovery of Man. And it takes place some 30,000 to 50,000 years in the future, where really humanity has truly evolved into something different. And it's that. And so the books are almost like dreams in a sense. They're myths. And because that's the real problem for those of us in technosignatures. We know, we can show mathematically that odds are any civilization that we get evidence of is going to be older than us.
Mm-hmm. Maybe you can explain why that is, because of the speed limit of light and the length of time a civilization we think would have had to exist to develop the kind of technology that would be recognizable by humans.
It's really more about just the fact that the odds are, right? If I'm looking for civilizations I've got a bunch of civilizations that last for 10 years, and I've got another bunch of civilizations that last for 1,000,000 years, I just have a better chance of, when I'm looking, of seeing the 1,000,000-year civilizations, the overlap, right, in time when I'm looking and when they exist. If they're all 10-year civilizations, then I just have to really get lucky that I just happened to look at that planet when that 10-year period was happening. So odds are we'd probably find a civilization that is much older than us. And what does that mean? Like, what does it mean for a civilization to last 100 million years, right? That's a really open question, which we only have begun to think about in any kind of sophisticated way. So, but and this is where the mature technosphere comes back into it, right? The mature biosphere lasted for geological timescales. It's lasted for billions of years, and it has been part of that lasting is its robustness, right? It's survived meteor impacts. It survived, volcanic upwellings of apocalyptic, right? We went through like 5 mass extinctions, and it came back every time. I mean, it's really hard to hurt the biosphere, right? Which goes back to the point about the task in front of us with right now is not to save the Earth. I really push back on that. The Earth is not a fragile bunny, that we have to protect. The Earth is a god or goddess that you don't want to piss off because it'll wipe you out in a second and just move on. So the biosphere has figured out how to exist on geologic timescales. And what we want is a technosphere that is robust enough to exist on geologic timescales. And so that's probably what we'll find. So, so it's funny how these problems of astrobiology circle right back to the problem of dealing with the Anthropocene, right? Mm-hmm. We're trying to figure out how to build what we're actually looking for, what we think is the thing we'll find if we find it.
Mm-hmm. So, I hadn't actually thought that more recent science fiction, that our solar system has had a renaissance recently as the focal point of storytelling. And as it turns out, we've barely explored our local solar system. It's not familiar to us at all. There could be many strange possibilities of life that we don't know it in our very backyard. The history of this, so going back to Liederberg and the space biology program in the late 1950s, and of course the Soviets were very interested in that too. Really fizzled after the inconclusive results of the Viking missions that landed on Mars, which is such a tragedy for scientific knowledge. It wasn't until 20 years later, that exoplanets really got picked up, that opened up this huge new possibility space of imagining what could be out there. And I'm just so excited about upcoming missions that NASA and ESA and even private space companies are planning the Europa Clipper mission just launched.
Well, the New York Times op-ed that you did, that was great about Enceladus and Europa. And these possibilities of, we've got these moons orbiting the giant planets that have more water on them than Earth.
Right.
So it's like what? It's like a 60-mile deep ocean under a 10-mile deep, thick layer of ice on Europa that's been there for 4 billion years.
And it's such an exciting place for life to perhaps have sparked because, okay, we think of Europa, I mean, it's very, very, very cold. I mean, for humans, it's not habitable. But if you go under this thick ice shell, the water, we're almost sure, is very warm by the hydrothermal vents. And that's a result of the push-pull and the tidal heating caused by
Jupiter.
By Jupiter. And so the possibility of life in Europa, which is inhabitable to humans, is really kind of even changing the concept of what a planet is and could be, and what kinds of planets would be very ripe for life. And so, now I'm thinking of the Haitian worlds, the portmanteau of hydrogen and oxygen they still remain like hypothetical objects. We'll see very soon with the James Webb Space Telescope, but just the myriad possibilities of biospheres is really like mind-blowing.
Mind-blowing. Well, the coolest thing about the exoplanet revolution, as you point out, so, the 1995, we discover our first planet orbiting another star. When I was a graduate student in 1988 and, early 90s, we didn't know whether there were other planets. In 1995, we finally, 2005. How often does a 2,500-year-old question get answered? Like in our lifetime, that question was answered. And now we know that every star in the sky has a family of worlds orbiting it. And, and then the knowledge, just cascades. Now we know that the most common kind of planet in the universe is the one kind we don't even have in our solar system.
Right.
In the solar system, you've got Earth. Earth is one Earth mass, and then you've got Neptune and Uranus, which are like 14 and 17, right?
Mm-hmm.
And there's nothing in between. There's no planet that has like 5 Earth masses. Turns out that's the most common kind of planet in the universe, what we call either super Earths or sub-Neptunes.
Mm-hmm.
So what are these worlds? What are they like? Could you have life on them? There's a project we're working on at the University of Rochester. We've got this giant laser. I swear to God, it's the size of a football field. And it's used to do fusion research where, you use the laser and you smack a little tablet of hydrogen to try and squeeze it down to to fuse, right, for power. But you can also use it to try and squeeze silicon to super high pressures that you get inside like a super Earth. Because we don't even understand what, if I've got 5 Earth masses of rock, what happens down deep? So we're exploring these possibilities of can these planets can a super Earth have plate tectonics?
Mm-hmm.
Because we think plate tectonics is really important for life.
And volcanism too, right? You need just the right amount of chaos, we think. So how we know life on Earth and then trying to project it onto alien possibilities, we almost basically, in the cosmic scheme of things, learned like a millisecond ago that most stars have planets, that most stars are actually not yellow dwarfs like our sun, but are cooler like red dwarfs.
Yeah.
Then there are orange dwarfs, which are in between. And so what we has historically defined as the habitable zone, it's the Goldilocks zone. It's not too hot, it's not too cold, and it's like just close enough to the sun. Now we can imagine exosolar systems that have these super Earths or sub-Neptunes.
Perpetual, one side's in perpetual daylight and one side's in perpetual night.
Yeah, so what are we going to find soon? And as a historian, I must decline making any predictions.
Right.
So I put that onus on you.
Yeah. Well, so first of all, I mean, the cool thing about what's happening is the surprise. We're being surprised all the time. So you mentioned these Haitian worlds. So let's use that as an example. So Haitian means hydrogen ocean. So these are planets, and literally 4 years ago, nobody thought of this, right? 4 years ago, nobody had ever talked about Haitian worlds, and it was an idea that a group of astronomers at Oxford actually came up with, which is that you could have things like a sub-Neptune, a planet that's maybe 9 times the mass of Earth, and a planet that's big enough that you would probably retain a lot of hydrogen gas as an atmosphere, right? So you'll have a rocky core. The core will be made out of rock stuff. And then there's going to be like a pretty thick layer of hydrogen gas on top of it that won't escape. Like Earth probably started with a hydrogen atmosphere, but the hydrogen's really light. It just bounces away into space. But this is a planet that's big enough, its gravity is going to hold the hydrogen atmosphere. And hydrogen is a great greenhouse gas, which means that the hydrogen atmosphere will keep the planet warm enough that if there's water on there, the water stays liquid, doesn't turn into ice. And so you have got this, you could have a 700-mile deep ocean. Our oceans are 6 miles deep, right? So at most, that's the deepest part of the ocean. So this is like 100 times deeper than Earth's oceans. And it's just an entirely new kind of world. And so the first James Webb Space Telescope data came down. We looked at some K2-18b. I love that. I love the telephone numbers that we have for these planets. So there's a planet out there that we've taken data from. It's out there. It's a place. And it actually, the extraordinary data, such high quality, actually points to it being a Hycean world. We don't know yet. We got to do a lot more, but it actually fit the models of a hydrogen ocean world. So the important point here is like, holy crap. 5 years ago, nobody was even talking about these worlds. And now sudden, boing, it's an entirely new class of planet that nobody's ever thought about. So I expect there to be nothing but that kind of surprise. So you talked about what we call brown dwarf, or not brown dwarf worlds, but M dwarf, so for people to understand what that is. So the majority of stars in the Earth, the sun is not an average star. The sun is actually, the sun is kind of heavy. The average star, the average mass of a star is about half of the sun's mass, which means it's actually much smaller and dimmer and cooler, which means it's redder. Our sun is nice and yellow, but these stars are going to kind of be dwarfs. They'll be small and they'll be red. They won't put out a lot of energy. And that means the place where, if you want to have a planet where the surface temperature is right for water, so that it's, a nice, comfortable 60 degrees Fahrenheit, you need to be very close to the star. What we call the habitable zone is very close. So this is nothing like when we usually imagine solar systems. This thing, it takes 365 days for the Earth to go around the sun. These things go around the sun on like a week. They're just zipping around the sun. And they're so close to the sun that, they get tidally locked so that their day, how fast they spin on their own axis, just like the Earth spins 24 hours on its axis, gets locked into their year. So, they're always showing the same face to the sun, just like the moon. We never see the back of the moon. It's always the same face. So what that means is one side of the planet always faces the sun and the other side always faces backwards. So one side is always in daylight, the other side is dark. And is it even possible to have life on those planets?
I want you to spin it out for us. Let's imagine that there was life. Okay, so given what we know about physics, chemistry, biology, geology, we have an M dwarf type and a tidally locked planet that is in the relative habitable zone of that star, and it has a solvent, which we think is fundamental.
Right, like some kind of water or ammonia or something.
Yeah, it doesn't have to be water, right? Which is, again, how we used to define the habitable zone, is like a planet that has liquid water. What is speculative yet plausible on this alien planet? Yeah,
totally different. So imagine a world where the sun is just always at noon. Like, that's just it. The sun never moves. Could you imagine that? And there's no night, unless you went to the other side, unless you took the trip to the other side of the planet, you didn't even know what darkness was. There was no night sky, unless you went to the place where there was night sky. So even that is super weird. And the cool thing about science is that, there's a whole cottage industry of people who run climate simulations on these worlds. And what you find is that in the subsolar point, the place where the sun is, actually probably will never see the sun because clouds always form there. There's always a dense layer of clouds right under the sun. You might think the dark side of the planet would just be freezing cold and the night side the night side would be freezing cold and the day side would be super hot. But because these things are, orbiting so fast, they're going around in, 4-day orbits, that actually means it generates winds. And there's winds that go from the day side, right under the sun, where the sun is just sitting there, and they circulate around the entire planet. So actually the night sides they're still cold, but they may not be so cold that the atmosphere just freezes out. Right. So they'd be very weird worlds. Right. But they certainly, you could have life. Why not? Like you'd have the source of energy, which is the sun. It would be red wavelengths. So that means that you wouldn't have green plant. Like photosynthesis would have to work with this longer wavelength red light rather than.
Tell us a little bit more of the technical details of that, how that works.
Yeah. So, on Earth, the plants photosynthesis occurs by taking the sunlight, which is peaks in the yellow part of the spectrum, and it takes the photons, the light particles, and it absorbs them and does this chemical shenanigans to be able to, produce a sugar molecule out of that. So the same thing would have to happen here, but now it's got a different kind of, the sun, the light from that sun is going to be kind of almost in the infrared. It's going to be longer wavelengths, which means it's going to be less energy per light particle. So it would have to work that out. The life would have to have a different kind of chemical shenanigans to a little dance that it would do in order to make sugars or whatever, some kind of energy carrying molecule.
So now I'm thinking about this as Adam's weird world. So we could call it awe. That lots of chemical shenanigans.
A lot of shenanigans. There's always a lot of shenanigans going on.
So many shenanigans. Okay. So and then it's so this kind of actual imaginative world building that you're telling me now is so important for astrobiology to make progress. I want to push you just a little bit more in terms of helping us flesh out, okay, what would be the marine plants? Like what color would they be? Like what would the sky, like the sun would be very close. It would be red wavelengths. What would it be like in the liminal zone between this day and night?
That would be such a weird place. The Terminator, what they call it, the Terminator, between the permanent place where the daylight turns into darkness. It would be kind of this weird, twilight, right? Imagine a world, a place where it's always that weird twilight where the color is bleeding out. Those details, it's, people are doing this, right? Because they're trying. Because if we're going to look, if we're actually going to look at these planets, and we can see these planets, we can't map them, but we get light from these planets. We can, and that's how we're going to do biosignatures or technosignatures. We can get the light that is either passing through the atmosphere or bouncing off the atmosphere, or bouncing off the surface from these planets, and we can analyze it and we can look for signatures of this life, and that's how we're going to detect life on other planets. So people are trying to work this all out. So, the details, woof. But I guess the thing I'd want to pass along to people is that these are places. What they have to recognize is, when they look up at the night sky and look at stars, there's just all these infinite places to be, with stories that are happening right now. Some of those worlds, if we look at, there'll be snow falling in, mountain passes, and there'll be clouds drifting through valleys. And, it's just what's been amazing about the exoplanet revolution, as I call it, and where astrobiology is now, is we recognize that the Earth is just one place. It's just one place to stand. There are so many places and so many stories, literally trillions of them, that it both makes the Earth more sacred, and it also makes us recognize, that there may be an entire, cosmic community of life that we are part of, that we are one, instance of.
Adam, thank you so much. It's been just a pleasure to talk to you, and my world has expanded for sure.
Well, thank you, Claire. This was a really fun conversation. I really enjoyed it.
See you on Planet Awe.
Futurology is a Studio B and Waveland production with distribution from Realm. Our executive producers are Nicholas Bergruin, Nathan Gardells, Dawn Nakagawa, Nils Gilman, and Jason Hoke. Futurology is produced by Grant Slater, Alex Gardells, and Natalia Ramos. Our associate producer is Alyssa Mardini. Futurology's theme music was composed by Marcus Bagala. The show is mixed and mastered by Aaron Bastinelli. Special thanks to Heather Mason, Olivia De Rienzo, Carly Migliori, and Nick Goddard.